Okay, so this is a joint work with Jalek Stark. I'll be telling you about separation of finite and infinite dimensional quantum correlations. So it seems that the program committee had some kind of a little team going on for today, because we started with an opening talk by Avishai Tal, who told us about his great result with Ran-Raz, about an oracle separation between BQP and the polynomial hierarchy. And we conclude with another separation. This one is between finite and infinite dimensional quantum correlations. These are known as CQ and CQS. There's another separation that is on everyone's mind, and we all wish to see resolved, but unfortunately I won't be resolving in this talk, which is this one. Okay, let me move on. Okay, so I'll start by giving you some basic notions. I'll define correlations, and then I'll be able to tell you about our main result. I'll spend some time discussing the main technique that gives us this proof of separation, which is device-independent self-testing. And then I'll try to convey some of the most important ideas that go into the proof of separation. And finally, I'll conclude. I'll give you some outlook. So, okay, let's get started. So what is a correlation? So this is the setup. We have finite question and answer sets. You can call them capital X, capital Y, A and B. You can think of X and Y as question sets, and A and B as answer sets. And the setup is as follows. So there's a verifier on the left, and two provers here, JALX1 and JALX2. And the verifier, who is classical, okay, so first the two provers, we're assuming that they're non-communicating, okay? And the verifier picks questions X and Y from capital X and capital Y, and gets back answers A and B. And you can think of the two provers as playing sort of cooperatively a game that is refereed by the verifier. And you can think that fixing a strategy of the two provers determines a probability distribution of answers given questions, okay? And we refer to this as a correlation. So more precisely, we say that a correlation is just an ensemble of distributions. There is one distribution for each possible question XY. So these are distributions over answers A and B, okay? So now, what is a quantum correlation? A quantum correlation is just a correlation that can be attained by a quantum strategy. And by a quantum strategy, okay, we mean that we allow the two provers to share some entanglement. And we say that the quantum strategy is specified by a joint state psi of the two provers. So we assume here that the two provers are each possessing one register. So prover 1 has HA, some Hilbert space HA, and the second prover has HB. And we assume that there's this tensor product decomposition. And then moreover, the first prover has a set of projective measurements. Okay, so there is one projective measurement for each possible question X in capital X, and likewise for the second prover. And you can think of their strategy simply as being, upon receipt of question X in capital X, prover 1 just measures, picks the corresponding measurement for question X and applies it to his half of the joint state psi, and then gets the answer. So if the two provers do this, then you can very naturally see that the probability of seeing answers A and B, given that the two provers received questions X and Y, is simply given by the overlap of the appropriate projectors onto the state psi. Okay. So when we define quantum correlations, what we're trying to capture is the power of the provers when we give to them quantum resources. Okay? And in general, I mean, it's clear that entanglement is the fundamental resource, okay? But it's not exactly clear how we should formalize entanglement. So for example, one thing that you could already ask is, should we allow the register of the provers to be infinite dimensional, or should we restrict them to be finite dimensional? And second, I mean, does this even matter, right? So does the registers, being infinite dimensional, give the provers more expressiveness? And taking even another further step back, okay, you could say, okay, I mean, who decided that sort of the register of the provers should decompose as a tensor product? You know, a perfectly legitimate alternative proposal is just that the two provers share some Hilbert space H, okay, and there's a single state psi in H. And simply we require that the measurements of the provers are compatible, okay, so that they commute. And in fact, there are some branches of theoretical physics in which space-like separated measurements are taken simply to be commuting measurements. So in general, I would say that it's a fundamental question in the foundations of quantum mechanics or any physical theory to sort of understand which resources are more expressive than others and which are just as expressive as others. And this is sort of the standpoint that we take throughout this presentation. So in the next slide, let me define for you some correlation sets that arise from the discussion that we've just had. So of course, there is CC, which is the set of classical correlations. This is the set of correlations that can be attained by provers which do not share any entanglement. All that they share is some classical randomness that they might have obtained before the experiment began. There is CQ, which is the set of quantum correlations attainable by finite dimensional strategies. Okay, so when we assume that the registers of the provers are in tensor product, but they are finite dimensional. There is then CQS, which is the same thing except that we allow the register of the provers to be infinite dimensional. And I'll keep a table with these abbreviations on the next slide so that you can keep track. There is CQA, which is defined as the closure of CQ. So these are things that can be approximated arbitrarily well by correlations in CQ, by finite dimensional strategies. So you can think of this as limits of finite dimensional correlations. And then finally, there is CQC, which is sort of the most general set that we'll consider. It's a set of quantum correlations attainable in the commuting operator model. So where we just assume that the two provers observables commute and nothing else. Possibly infinite, yeah. Okay. So as promised, here's the table. You can keep track of the names. So what do we know about the relationship between these sets? Okay. So I think the most important thing that we know, which is also part of the reason why we're here, is that classical correlations are strictly contained in the quantum correlations. And this is, I would say, a landmark result in physics. It was shown by Bell in 1964. And it really does say that entanglement gives the provers more power. Okay, so it's really a fundamental resource. But then, okay, how do we formalize entanglement exactly? So the next containment, it's just a trivial containment. Okay, so finite dimensional quantum correlations are contained in the infinite dimensional ones. I'm not saying a strict containment, just a containment. The next non-trivial containment was shown by Scholz and Werner in 2008. And it tells us that the closure of CQ, which is CQA, okay, not only contains CQ by definition, but it also contains CQS. Okay? So you can think of this as saying that any infinite dimensional quantum correlation can be approximated arbitrarily well by finite dimensional quantum correlations. And this is a non-trivial result. Okay, but intuitively you can think that if you have a correlation that is attainable in infinite dimensions, you can sort of truncate the state that attains it, and you'll get better and better approximations. It's not so simple, but this is just an intuition. And then CQC is the set that is most general and contains everything else, is a set of correlations attainable in the commuting operator model. Okay, so I'll keep this list of containments at the top. So the question is, do we know of any other equality or strict separation other than the one given by Bell's theorem? So we did not know of any until the recent breakthrough work of William Slofstra, who showed us that CQS is not equal to CQC. So in other words, there are correlations that are attainable in the commuting operator model, which cannot be attained in the tensor product model. And this was presented at QIP, I think 2 years ago. And then William Slofstra was kind enough to strengthen this result to CQS not equal to CQA. And this shows that the set of quantum correlations in the tensor product model is not closed. There was another proof of this result later that year by Dikema, Paulsen, and Prakash, which had slightly smaller, I mean, actually much smaller question and answer sets. Okay, so if we wanted to solve something now, what could we solve? So what is still open? So we could try to solve the last inclusion, which asks whether CQA is equal to CQC. Okay? This is known that CQA equals CQC if and only if Kahn's embedding conjecture is true. And this is a major open problem in operator algebras. So you know, maybe some other day. And the other inclusion that is still open is the first quantum one, which asks whether finite dimensional quantum correlations are contained in the, strictly contained in the infinite dimensional ones, or they're equal. And this seems somewhat more approachable. And it's the question that we address in this work. So let me give you some context about this question. So what do we do? We know anything. So first, if you consider the simplest example, so the case where the question and answer sets all have size 2, okay, it is well known that the two sets are equal. So infinite dimensions do not give you any extra power. And this is a result by Luis Mazanes. And it uses, amongst other things, an application of Jordan's lemma. And in fact, it is not only the case that you can attain everything in finite dimensions, but it's enough to just have mixed states of qubits. And you can get everything in this 2-2-2 scenario. So then, okay, let me just clarify one thing in case it's not clear. So I'm defining CQ to be the union of the finite dimensional quantum correlations, union over all possible question and answer set sizes, okay? So showing a separation at any level would imply, likewise for CQS, okay? So showing a separation at any level would imply that CQ is not equal to CQS. This is just a clarification. So what about larger question and answer sets, okay? So the next possible thing that we can consider is 3-3-2-2, okay? Question sets of size 3 and answer sets of size 2. And already here we're a bit stuck, okay? There is a famous or infamous Bell inequality, which is known as I3322. It was introduced by Froissart in 1981, and it was studied extensively by Pal and Vertesi, who gave a lot of numerical results. And this led them to conjecture that the maximal violation of this Bell inequality is attained exactly in infinite dimensions, but cannot be attained in finite dimensions. Okay, and they conjectured this because, so they ran a semi-definite programming hierarchy, this Navasquez-Pironi-Racine hierarchy, and they got an upper bound on the maximal violation, and then they tried to match this upper bound from below. They came up with some ansatz, some finite dimensional ansatz of a strategy, and they realized that as they increase the dimension of this ansatz, they get closer and closer to the upper bound, but they can't quite close it exactly, and that's why they conjectured that you only close it in infinite dimensions. Okay, but at the same time, you know, it's not clear that their ansatz is optimal, so it could still be that there's a better, I mean, the optimal ansatz actually does close the gap, and it's finite dimensional, so the two sets could still be equal. Okay, so we don't know. And what about for larger question sets? Well, there's really no evidence either way. So the question is wide open. And so we tried to resolve this, and after much effort and thought, this is our result as anticipated, that finite dimensional quantum correlations are not equal to infinite dimensional quantum correlations. And we show this by exhibiting explicitly a correlation on question sets of size 4 and 5 and answer sets of size 3 that is attained exactly in infinite dimensions, but no finite dimensional strategy can attain. So in the next portion of the presentation, I will tell you about the main technique that makes this result come true, which is self-testing, okay? And before I do that, let me just introduce one extra piece of notation. It's very simple, okay? So you can specify completely a correlation by specifying for each possible question xy a table, okay, with entries probability of AB given xy, where the rows are the A's and the columns are the B's. Okay, this specifies the correlation completely, so keep this notation in mind. And now on to the main technique, which is self-testing, okay? So you've already heard about self-testing a few times. So informally, device-independent self-testing refers to the certification of quantum states and measurements based solely on the observed correlations. Okay, so we are in the setup, the same setup that I just described with a classical verifier and two or more potentially untrusted provers that don't communicate. And the verifier would like to exert some kind of control on the two provers and get some guarantees about which states and measurements are they performing, okay? So you can envision that, I mean, having such a result, as any self-testing result, could be useful in quantum cryptography. In fact, it is. And self-testing has found applications in randomness expansion, quantum key distribution, and even delegated quantum computation. So here's a little bit more precise definition of self-testing. So fix some question and answer sets, X, Y, A, and B, okay? We say that a correlation P star on these question and answer sets self-tests a quantum strategy, which is given as so, okay? If up to local isometries, this is the unique strategy that attains P star, okay? And I'm saying up to local isometries because this is somewhat of an irreducible degree of freedom in the sense that the two provers can always apply a local change of basis, and this will not be detected in the probability distribution of the answers given the questions, okay? But up to local isometries, this has to be the unique strategy that attains P star. And if this is the case, then we say that P star self-tests it, okay? So let me be a bit more concrete with an example. Of course, the most famous example of self-testing is given by the CSH game. And now it's Thursday afternoon at QIP. So by now you've already heard the CSH game introduced and mentioned several times. So in particular once by Matt Coudron. So I won't repeat it again. Instead, I'll just pull up Matt's slide. Okay, let me, for some self-containment, I'll just describe it real quick. So CSH game is on question and answer sets of size 2. And then again, the verifier picks questions X and Y, gets answers A and B. And we say that the two provers win the game if the XOR of their answers equals to the end of the questions. We all know that the optimal classical success probability in this game is 3/4 when the questions are chosen uniformly at random. But if they are allowed to share entanglement, then the provers can do better. They can reach cos squared pi over 8, which is roughly 85%. And what is important to us is that if the provers are playing a strategy that has optimal winning probability, then they must be sharing an EPR pair. Okay, this is the only way that they can do it. They have to have a pair of maximally entangled qubits, and they have to be performing these ideal measurements. Okay, it's not important what they are. It's important that they are unique up to local isometries. And there's an equivalent formulation of CSH, which is, I'm sure many of you have already seen, which is the CSH inequality, okay? It's equivalent in the sense that it's just obtained by considering the expected score of the provers in the game. The left-hand side of this inequality looks like this. And then when psi is restricted to be a product state, 2 is the upper bound, okay? This is the classical bound. If we allow psi to be entangled, then we can reach 2 square root of 2. And as you can expect, any correlation that attains maximal violation or attains this bound self-tests the EPR pair, okay? There is a nice generalization of the CSH inequality, which is very important to our work. It's called the tilted CSH inequality. It was introduced by Asin, Massar, and Pironio in 2012. Okay, so in short, it's known as just tilted CSH. So let me again pull up Matt's slide. Okay. This is the last joke that I have. Okay, so it's very similar to CSH. It just has an extra term beta alpha 0 on the left-hand side, which gives an extra beta on the right-hand side. Beta A0, sorry. The quantum bound is square root of 8 plus 2 beta squared. And it turns out that any correlation that attains this quantum bound self-tests what is known as the tilted DPR pair, okay, which is cos theta 0, 0 plus sin theta 1, 1, where the angle theta and the parameter beta are just related by some invertible function, okay? And for convenience, I'm most interested in the ratio between cos theta and sin theta. Okay, so I'll refer to the tilted CSH for ratio alpha as the one that self-tests this tilted pair, where the 0, 0 and the 1, 1 coefficient are in ratio alpha. Okay, so this is the basic of self-testing, okay? I mean, one thing that is nice about tilted CSH, it tells us that for any pair of entangled qubits, okay, any pair of partially entangled qubits, there exists a correlation that self-tests it, okay? So this is quite nice. And now, finally, okay, let me tell you about a self-testing result that is connected to our proof of separation, okay? So one very natural question to ask is, is it possible to self-test more than just pairs of entangled qubits? Okay, can you self-test more? Can you self-test higher dimensional things or other special states? And it turns out that over the years, several examples of states have been given, okay, which are self-testable. But for a while, it was open whether we can actually self-test everything in the bipartite case. And it turns out that, in fact, you can self-test any pure bipartite entangled state of any finite local dimension. And this is a result from a joint work with Kuntongo and Valerio Scarani, where we show that for any pure bipartite entangled state, and you can write it in this form in a Schmidt basis, okay? So up to a local change of basis, any pure bipartite entangled state can be written like this. For any such state, there exists a correlation on question sets of size 3 and 4, and answer sets of size D, where D is the local dimension, that self-tests it. So another way to sort of view this result pictorially, or to interpret this result, is to think that for any pure bipartite entangled state, or any such state, possesses a classical fingerprint, or a classical footprint, if you will, okay, that singles it out uniquely, okay? Good. So in the next few slides, I'm gonna tell you a bit about the important ideas at a high level that go into proving this self-testing result, because they're intimately related to our proof of separation. So here they are. So the main recurring idea in proving this self-testing result is the following, okay? One very fruitful point of view is looking at this generic state with Schmidt coefficients Ci as a direct sum of tilted DPR pairs, and to exploit the tilted CSH self-test on each of the pairs, okay? So now each of the pairs will have a different ratio between the coefficients, and the ratio is determined by the CIs, okay? And you can decompose a generic state in such a direct sum of tilted DPR pairs in two ways. One is starting from 0 in blue, and one is starting from 1, okay? And taking a step back, in general, when we are trying to come up with a correlation that self-tests a state, a typical approach is to try and come up with ideal observables, okay, that when measured on this state, produce a correlation that tries to capture the essential properties of the state that we want to self-test. So in this case, we hope that this view as a direct sum of tilted DPR pairs captures the essential properties of this state, and it's enough to single it out. So here is the self-testing correlation for such a generic state. As I anticipated, it's on question sets of size 3 and 4, and answer sets of size D. Okay? And I'll describe it to you by telling you what the ideal observables are that attain this self-testing correlation. And the ideal observable themselves, they mimic this intuition that I've discussed in the previous slide, okay? So we take them to be direct sums of single qubit ideal tilde CSH observables. So they look like this. They are block diagonal with 2 by 2 blocks. And each block, each 2 by 2 block contains ideal single qubit tilde CSH observables on the computational basis elements 2m and 2m plus 1. And each of these tilde CSHs has a different ratio, which is determined by the Schmidt coefficients Ci of the state that we want to self-test. So this is for one subset of questions. And then for questions x in 0, 2 and y into 3, we take them to also have a direct sum decomposition in 2 by 2 blocks, except that it's shifted forward by one computational basis element. And this sort of mimics the two decompositions that I talked about in the previous slide. And as you can expect, if we pick these ideal observables, then the structure that we have here will be reflected also in the correlation tables that they generate. Okay, so the correlation tables themselves, so recall that the entries of these correlation tables are the P, AB given XY. Okay, so they also have a block diagonal form with 2 by 2 blocks. In blue for questions XY in 0, 1, and in red for questions X in 0, 2 and Y into 3. So, I mean, the punchline is, the takeaway is that anyways, this 3,4-DD correlation that I described to you self-tests the state that we wanted to self-test, okay? So, how does self-testing or this self-testing result help us in proving the separation of CQ and CQS, okay? This is what I'll tell you in the next few slides. So if you have momentarily zoned out, you can tune back in. So all that you need to know so far, I mean, the important thing is that for any pure bipartite entangled state, there exists a correlation. I can write down a correlation on question sets of size 3 and 4 and answer sets of size D that can be uniquely attained by that state, okay? So now consider making a particular choice of these coefficients Ci, okay? Pick them to be Ci equals alpha to the I for some alpha in 0, 1. So pick the Schmidt coefficients to have a nice geometric progression and consider the 3,4-DD correlation that self-tests this state, okay? Now think of generalizing this correlation by taking a limit as D tends to infinity and seeing what happens, okay? So we're trying to go from a correlation on 3,4-DD to 3,4 infinity infinity. So you might wonder, first of all, does this even make formal sense? Yes, it does, okay? So simply we're going to an infinite dimensional Hilbert space. The ideal state is now a sum of alpha to the I, ranging from I equals 0 to infinity. And the ideal observables have the same form that they had before. They are block diagonal with 2 by 2 blocks, except that now they live on an infinite dimensional Hilbert space. But now, because we made a particular choice of the Schmidt coefficients, we took them to have a nice geometric progression. Now, what happens is that all of the 2 by 2 blocks have ideal single qubit tilde CSH observables for the same ratio alpha, okay? And this is a result from a previous work with Jalex. This 3,4 infinity-infinity correlation can be attained in infinite dimensions. This is the strategy that attains it, but cannot be attained in finite dimensions. So you might be wondering whether this already gives us separation of CQ and CQS. The answer is no, because in the original formulation of that question, we assumed that the question sets and the answer sets are finite. Here, the answer sets are countably infinite. And intuitively, you can think that the larger the question and answer sets are, the easier it is for the power of infinite dimensions to be expressed, okay? And in fact, here we have answer sets of countably infinite size. So to recap what we have so far, on one end of the spectrum, we have the simplest scenario, the 2 to 2, 2. In this case, finite and infinite dimensional quantum correlations are the same. On the other end of the spectrum, I just argued that in the 3, 4 infinity, infinity case, there's a separation, they're different. Now, in between, we basically know nothing. The next simplest example that we can consider is the 3, 3, 2, 2. Okay? So in this case, I told you that there is this mystery around the I3322 Bell inequality, which has so far eluded everyone. But it's conjectured that the two sets are different. What we show is that if you go to slightly larger question and answer sets, 4, 5, 3, and 3, you get a separation between finite and infinite dimensional quantum correlations. So basically, for the rest of this talk, I will give you a sketch of the most important ideas on how we go from a separation on 3, 4, infinity, infinity, to a separation on 4, 5, 3, 3. So before I do that, let me just say one more word about why it is easier to show a separation when you're allowed to have countably infinite answer sets. Okay? So for the self-testing result with Kun-Tong Go and Valerio Scarani, it was crucial that the correlation was on answer sets of size D. Okay? This is because any strategy S that attains this correlation, okay, would have to consist, by definition, of projective measurements with the outcomes, okay, by definition. And this helps a lot in enforcing that the underlying joint state must have dimension D. Likewise, in the 3, 4 infinity, infinity case, okay, we know that the strategy attaining the ideal correlation must consist of projective measurements with infinitely many outcomes. And this helps a lot in enforcing an underlying state of infinite dimension. Now, when we go to everything finite, we have none of this help. Okay? So the real question is it possible to pack into just finitely many outcomes enough structure to make infinite dimensions necessary? And one observation is that we haven't really exploited the fact that every tilted pair has the same ratio alpha. There seems to be some redundancy, some symmetry that we have not exploited, and we really need to exploit some symmetry if we want to pack enough structure into just finitely many outcomes. So in the next slide, I'll just show you, or give you an idea of how we exploit this symmetry. So remember that our ideal state had Schmidt coefficients that are in this nice geometric progression. And now, the first thing that I want you to notice is the following. Take our ideal state on the left-hand side. Now, notice that it is local isometry equivalent. Okay? In fact, it is equal to the state on the right-hand side, okay? Where aux is some auxiliary state. Why is that? Okay, you can just think of doing the direct sum decomposition into tilted EPR pair that I mentioned earlier. Now, every tilted EPR pair will have the same ratio alpha. So essentially, you are just factoring out the tilted EPR pair and dumping everything else into an auxiliary state. Okay, so this equality should be clear. But notice also that the state on the left-hand side is also local isometry equivalent to the state in 2. Okay? Where in 2, we have just left out the first term, 0, 0. And then we've done the same factorization as we did in 1, okay, where we pulled out an EPR pair. Okay? Now, recall that local isometries do not change the set of Schmidt coefficients. Okay, it's preserved. So what I claim is that any state that is local isometry equivalent to both 1 and 2 must have infinitely many Schmidt coefficients. Why is that? Oops. Why is that? Because from the first expression, the Schmidt coefficient of the state must be in even number, okay? Because they come in pairs, right? The Schmidt coefficients of the expression 1 are the Schmidt coefficients of aux multiplied by 0 or by alpha, so they come in pairs. But from the second expression, the number of Schmidt coefficients has to be odd, because we have left out 0, 0, and then we have an even number here. Okay? This can only be possible if the set of Schmidt coefficients is infinite. Okay? So this is one piece of intuition that you can hang on to. Okay? And now let me show you how we can use this intuition to get a cartoon proof of our separation. I call it cartoon proof because it uses some magic. It's not a full proof. Okay? But our cartoon proof goes like this. We will introduce some ideal correlation P star. Okay? And suppose that by magic, we knew that any state psi attaining P star must be such that the following two things happen. Okay? Psi is local isometry equivalent to this state here, which is the same that we had earlier. But we also know by magic that psi has to be local isometry equivalent to the state in 2 for some separable state phi. Okay? So suppose that we know that phi is separable. Then we can apply the same intuition from the previous slide, right? Suppose for a contradiction that this state psi was finite dimensional, then from the expression 1, it would have to have even Schmidt rank, and from 2, the Schmidt rank would have to be odd. So this is impossible. So psi has to be infinite dimensional. Okay? Now, of course, here the magic happens when we assume that phi is separable. In general, we can never assume this, because the provers can always tensor some auxiliary state to phi, and just ignore that state, okay? But nonetheless, the state is there, and it has an arbitrary number of Schmidt coefficients, and that will sort of mess up the argument, okay? So all that we can say in general is that psi will be local isometry equivalent to something like this, and this is not necessarily separable. So the argument that we had before wouldn't go through. So in our real proof, we will still introduce some correlation P star. We will still argue that any psi attaining P star must decompose in two similar ways, as so. Okay? But we will need a more careful argument to understand the relationship between the Schmidt coefficients here and here. Okay? And we'll still argue that they have to be infinite dimensional. So, and I guess along the way, we will basically add a few questions. That's why, I mean, if you have noticed, we go from 3-4 to 4-5. Okay, we had some few questions, but those are some details. I mean, they're important, but there are details. Okay, so now let me describe to you the separating correlation, finally. I'll describe it to you by giving you the ideal state and the ideal measurements that attain it. Okay, so the ideal state, as we have discussed, it's this sum of alpha to the I from 0 to infinity. The ideal observables have the same form as they had in the 3-4 infinity case. They are still block diagonal with 2x2 blocks. But now the important thing is that before, we were allowed to have infinitely many answers, okay? So we were allowed to map all of these eigenspaces to infinitely many outcomes. Now we can only map them to just 3. Well, to finitely many, but we do it for 3, okay? So we have to somehow map the outcomes, the countably infinite outcomes that we had before, to just 3. And this is where we exploit the symmetry. So this is how we do it. So for the first subset of questions, x, y, and 0, 1, we map the outcomes that we had before, okay, in the following way. So we map the even ones to 0 and the odd ones to 1. So we don't use the third outcome, 2. And this induces the following correlation table, which is just on answer sets of size 3, where in the top left 2x2 block, we have the ideal tilde CSH correlation for ratio alpha. And here is where we have exploited the symmetry. This only works because the ratio in every pair is alpha. Okay? And you can sort of reasonably believe me when I say that any state psi that produces such a table would have to be local isometry equivalent to this expression here, which is the same that we had earlier. And then for the second subset of questions, x, y, and 2, 3, we do a very similar mapping, except that, so basically everything as before, except that the first answer 0 is mapped to 2. So this induces a slightly different correlation table, in which in the top left block, we have again the ideal tilde CSH correlation, but it's reweighted down, okay? And there is some weight also on the answer 2. And you can, again, sort of reasonably believe me that any state psi that that produces such a correlation table is also local isometry equivalent to this expression, which is the same one that we had before, okay? This 2 tensor aux plus this part here, which is basically the same as this. And now basically the reason why we need to introduce some extra questions, okay, and we go to 4 and 5 from 3 and 4, is that we need to somehow patch up these two decompositions. We need to make them sort of talk to each other. And okay, so for that we have extra questions, but at least I think that this gives you some intuition about, I guess, the important ideas in how we construct the separating correlation. Okay, so in summary, what I've shown to you is I've described to you a correlation which is on question sets of size 4 and 5, and answer sets of size 3. I argued that any strategy that attains it must be infinite dimensional. And moreover, I've described it to you by giving you explicitly the infinite dimensional strategy that attains it. And so this shows that CQ is not equal to CQS. Now, before you get your hopes up, can we use this separating correlation to construct a test for infinite dimensionality? Okay, so suppose that you have a device at home and it's a box, and you want to know whether inside the box there is actually an infinite dimensional state or it's just finite dimensional. Okay. Of course, we can't have such a test, at least not with our separating correlation, because our separating correlation can be approximated arbitrarily well by finite dimensional correlations or strategies. And so any statistical test that you can come up with will inevitably have some statistical noise, so you can always be fooled by a high enough but still finite dimensional strategy. Okay, so no, we cannot have such a test. And this is not the shortcoming just of our correlation. In general, I had told you at the beginning that any infinite dimensional quantum correlation can be approximated arbitrarily well by finite dimensional ones. Okay, CQS is contained in CQA. On the other hand, we do have tests for arbitrarily high but finite dimensional entanglement. So these are called the dimension witnesses. A dimension witness is simply some test, some non-local game, such that if the provers win with probability epsilon close to optimal, then this certifies that their strategy must have at least a certain amount of dimension depending on epsilon. Okay, so these I believe are the most efficient result. This one is from Slostar and Vidic for 2 players, and the other one is by Zhengfeng Zhi, Debbie Leung, and Vidic again. So this one, the second one is for 3 players, and you can actually test. I mean, it's a non-local game such that if you win it with probability epsilon close to optimal, then this certifies that the strategy of the provers must have exponential entanglement in, well, 2 to the 1 over epsilon or something. Okay, 2 to the some inverse polynomial in epsilon. So it is exponentially better than this one, but it requires 3 provers. Okay, so let me conclude with some open questions. So I think the most important question, at least to me, is what's the simplest scenario that exhibits a separation of finite and infinite dimensional quantum correlations? So the simplest possible is 3322, because in the 2222 case, I've told you that the 2 sets are equal, and I've mentioned the I3322 Bell inequality. I think it's a fascinating mystery, so I mean, if you have any idea or you want to talk about it, I'm happy to talk about that. Then there's this other question. I think I'm running a little bit late, so I'll just leave it on here. You can read this question. And then finally, there's the question of whether CQA is equal to CQC. Right, I told you at the start that this is equivalent. I mean, this is true if and only if Kahn's embedding conjecture is true. So I would say that this is only for the baldest amongst us. I would like to conclude on a motivational quote that I saw as I was actually walking yesterday on campus. which is this one. Thank you.
Is there another microphone? Oh, this one as well. Okay, maybe you can
By the way, it was a coincidence. I didn't know that they were giving this. I had this already prepared.
Indeed, both ways it was a coincidence. Well, thank you very much for this beautiful talk, which is unprecedented in clarity, I would say. Are there any questions? Yes, Daniel. I can give you. Oh, it's on the other side.
So, is there a reason that?
Wait a moment. So we can all hear it.
Is there a reason that the question size has to be the same? I mean, couldn't there be like a 3, 2, 2, 2?
Sorry, you mean the same? So in our example, they're 4 and 5.
Right. So you said the simplest one would be 3, 3, 2, 2 because the 2, 2, 2. So what about a 3?
Yeah,
2,
no,
2,
it's
2?
true. You're right. It could be 3, 2, 2. Yeah, that is true.
Right, excellent.
Oh, it cannot be? Oh, okay. No.
Any argument for this?
So we're just playing numbers here. But
Okay.
no, so I don't have any intuition as to other smaller sets. The only one that I've really looked into is 3322, because it turns out from the numerics of Pal and Vertesi, actually the ansatz that they have is very similar to our strategy. So it still has this block diagonal decomposition. So I've been looking into that. That's the only one that I've considered, basically.
Okay.
Any more questions? While you think about a question, I can of course ask, what happens if I have 3 parties instead of 2, just to change the numbers in a different way?
Well, so I mean, if you're asking about the separation, then with 3 parties, you still have the separation because you can just basically,
Sure.
I mean, ignore one party.
But what about smaller question size then?
No.
All right. Do we have any more non-trivial questions?
Yeah, sorry. I was wondering about, is there any difference between correlations in countably and uncountably infinite dimensional Hilbert spaces?
Oh, so I've told you basically that, well, I mean, the larger you make the question and answer sets, the easier it is for infinite dimensions to, to express their power. So, I mean, if you go, we already have a separation for countably infinite answer sets. So I think if you go to uncountably, I've not thought about that, but we already have a separation for countably infinite. Yeah.
Any more questions?
Yeah, I don't know if I can say more than that.
And any more questions? Okay, otherwise I'd suggest we thank our bold speaker.